So today's speaker is Professor Andreas Winter. Andreas Winter did his PhD at Bielefeld University in Germany under the supervision of mathematician Professor Rudolf Alschwede. He graduated in 1999 with a thesis entitled Coding Theorems of Quantum Information Theory. After his PhD, Andreas Winter moved to Bristol, where he worked first as a postdoc, then as a lecturer, and eventually as a professor. For his work at Bristol, he was awarded both the Leverhulme Prize in 2008 and the Whitehead Prize in 2012. 2012 was also the year when Andreas Winter relocated to Universitat Autònoma de Barcelona, where he now works as a professor of quantum information. Professor Andreas Winter's long publication record touches on most aspects of quantum information theory. Indeed, Andreas is one of the pioneers of this field. His most notable works concern the interplay between quantum entanglement and information theory. Last week, we heard from Professor Rafal Demkovich-Dobransky that adaptive strategies are of little value in quantum metrology. So today, we all hope that Andreas will restore the honor of adaptive strategies by instead applying them to channel discrimination tasks and seeing whether or not they can give us any value in those settings. So with these words, Andreas, the virtual floor is yours, and please feel free to take it away.
Okay, yeah, so well, thanks for the nice invitation, and also thanks for the patience. I guess most of the audience is aware that I was supposed to speak already a while ago because I had a terrible flu and was essentially without voice. I asked to defer it, and so now I'm finally catching up with my commitment. As we discussed with the seminar organizers, I'm going to talk about a relatively recent work. So the preprint is from, and I hope you can see the pointer, the preprint is from 2020, was recently published. This is joint work with Farzin Salek, who at the time was a PhD student in our group in Barcelona, and with Masahito Hayashi, who is, of course, well known in quantum information and in everything to do with hypothesis testing and estimation. And I must say, I learned a lot from him about this particular topic of hypothesis testing, and so I'm very happy that we managed to realize this joint work. Yeah, so title is quite longer than I wrote here. It's just a short one: Adaptiveness and Channel Discrimination. Okay, so I want to start with just a brief run through of the setup, like in sort of general statistical terms, and then we fill it in with our quantum mechanical specifics. So we will, for the talk, we will only consider binary hypothesis testing. So traditionally, this is often presented as a decision between something called the null hypothesis and the alternative hypothesis, because oftentimes there is an asymmetry between the two. But we also will consider the symmetric setting, that there are just two possible hypotheses about the world, so to speak, that we observe, and we just try to make a good choice between them. And so, generally speaking, we could say that the statistician's way of looking at this, well, you get to take some samples that have something to do with the hypothesis, and then you have to have a rule to choose between the two. And because everything is statistical, and the two hypotheses often are not perfectly distinguishable from the data that we have usually two kinds of error probabilities, namely the obvious ones. The true hypothesis might be the alternative, but our test opts for 0, the null hypothesis. So it means you're not recognizing the alternative hypothesis. And the other error probability that the null hypothesis is actually true and you're opting for the other. So you're falsely rejecting the null hypothesis. And because of the nature of this setup, I mean, every test will have these two error probabilities, but obviously we are interested in making both of them small, which we cannot because usually there's competition between them. If you make one of them smaller, you pay a price that the other becomes larger. And so kind of the kind of statistics that was created about 100 years ago, probably as a field, that's all about this. I mean, in this particular simple setting, and obviously things can be much more complicated if your hypothesis is not simple, for example, this probability might not be a well-defined number. It might depend on some other parameters, so we need to optimize. But we will not consider this. I mean, we make it as simple as possible. Everything is described by some giant probability distribution, and then those probabilities of error are well defined. So the other element is that we are going to look at the asymptotic setting, where you have access to many independent samples, whatever that means. In probability theory, that's what Kolmogorov axioms do for us. In the subsequent talk, we'll have to basically say what we mean by independent samples. In any case, if this independence somehow is related to the intuition that the errors go to zero and they go to zero exponentially, and so the trade-off is not so much between alpha and beta, because both of them will be asymptotically small, but between those exponents. We want both of them to be as large as possible, as C1 and C2. And again, there is competition between them. And so this is part of the general preparation. So if you know this is just, I'm basically just saying, let's agree on the vocabulary. There are sort of 2 or 3 regimes in which we can study this question. The Stein setting is, we are not so much interested in the error probability of first kind. All we want is that it goes to 0, so the C1 should be positive, but we would like to make C2 as large as possible. So this is usually called the asymmetric hypothesis testing setting, where you want to recognize the alternative hypothesis, for example, a rare disease with good probability, but above all, you don't want to assign the disease to healthy people. That's your null hypothesis, which are the majority. So you know that the prior between H1 and H0 is hugely biased in favor of H0, so you want to minimize the probability of rejecting it. In the symmetric setting, we are interested in the case when both of those exponents are the same, and we would like to minimize them kind of simultaneously, maximize them simultaneously. And Hoeffding, this is kind of the interpolation between them. We fix one of the 2 exponents, and we would like to make the other one as large as possible. So we want to find what's the relation between those 2 exponents. So this now, the first 2 things, they are just functions. They depend on the statistical nature of the hypothesis. They're numbers, and the last one is a function of this R. And kind of for R equals 0, we cover Stein, and for R equal to this supremum, we recover Chernoff. Okay, so this is kind of the general background. This is the setting in which we will move. And so for the rest of the talk, I want to basically discuss how this hypothesis testing looks like when our hypotheses are given by quantum objects. And so I will start with a brief review in part 1, when the hypotheses are quantum states. So like H0 is sigma, and H1 is state rho. And then I will move on to the channels. And so basically here's sort of the summary. The first thing is we will have to discuss what we mean by adaptive versus non-adaptive strategies, and I think that it's a slightly different the meaning of the word, or the slightly different interpretation of those notions compared to Raphael's talk last week. And so there is kind of it's done in such a way that the adaptive strategies to distinguish channel hypotheses are more powerful than the non-adaptive ones on paper, by definition. But it turns out that there are plenty of settings where the adaptiveness doesn't help. So kind of I'm going to review that in the Stein setting, and for certain classes of channels, all 3 of those asymptotic settings don't provide any kind of advantage in the asymptotics when we consider adaptiveness. But then the important part is the one written in green, at least important for me, that there is actually one setting for genuine quantum channels where we can show a quantitative advantage of adaptiveness. And so I hope I can also show you a little bit how you do this. So let's just go through quickly the review for of the hypothesis testing for states, because that's a topic that goes back to, well, the 90s, I would say. I mean, I was a bit stupid giving only the names here, but I mean, they carry, I mean, they are associated with these results here. Yeah, so the most general thing you can do if you have to distinguish between two states, well, you have to have a binary POVM, because you have to give one of two possible outcomes. I vote for rho or I vote for sigma. And so for this POVM, that's just, you know, positive matrix M, so that 1 minus M is also positive. And let's say M corresponds to voting for rho, and 1 minus M corresponds to voting for sigma. And because I want to consider this n copies, well, n copies of a state means you just got a single state rho tensor n, or a single state sigma tensor. So yeah, so these are by Born's rule, these are the probabilities of error for the given test. And so maybe the fundamental result that everybody should know in this whole kind of area is the quantum Stein's lemma that goes back to Fumio-Hiei and then Spätz, and was improved by Ogawa and Nagaoka. And the final statement is this one. If we're looking for the minimum beta such that alpha is kind of bounded away from 1, epsilon is supposed to be small, but could be fixed. You could also let it go to 0 in some slow way. If you're looking for this minimum beta, that's now a function of n. We are interested in the exponent, so we take the log and divide by n. This converges for every epsilon to this quantity here that is known as the quantum relative entropy, or maybe more precisely the Umegaki relative entropy, because it was proposed on purely formal terms in the 50s as a kind of extension of the phenomenon entropy. And this is the formula. It's trace rho log rho minus log sigma for the density matrices, which is well defined as long as the support of rho is contained in the support of sigma. And if that is not given, then we simply declare the value to be infinity. And with that declaration, this theorem also holds. If the relative entropy is infinite, then this limit here converges to infinity. So yeah, this is wonderful. So this operational interpretation of the quantum relative entropy as the asymptotic rate of distinguishing rho from sigma. And a little bit later, but also kind of already more than 15 years ago, Konrad Audenot et al. And then Nussbaum and Scholar, in a pair of papers, they proved the quantum Chernoff bound. So this is the case when we want both of the error probabilities to go to 0 equally fast. So the trick to impose this is that you look at the sum of the two. You want to minimize the sum. Again, you take the log and divide by n. That turns out that converges, and amazingly, we can actually characterize the limit. It's almost a closed formula. It's a single parameter optimization of this weird expression trace rho to the s sigma to the 1 minus s. So this is some sort of a parameterized fidelity between the two states. And we minimize this and we take the negative log. That's the exponent. And so remember, these are I'm always talking about the exponent, like how I know that all these error probabilities are exponential in n, so I want to know what is the exponent in front of the n. And so yeah, Hoeffding, quantum Hoeffding, that was done then immediately afterwards, like still about 15 years ago by Hayashi and Nagaoka. That's, like I said, you fix the the exponential behavior of one of the two error probabilities, let's say the first kind, and you want to minimize the error probability of the second kind. You know it's going to be exponential, so again, you take the log and divide by n. This has a limit, and it's given by this kind of transform of another quantity which is quite well studied by now, the Petz Rényi-Petz relative entropy for quantum states. So this defines the same trace rho to the s sigma to the 1 minus s that appears here. And okay, we take a log and normalize in some particular way. The normalization is essentially done in such a way that for s converging to 1, we recover the phenomenon entropy. And otherwise, it's kind of it's a normalization that makes sure that all of those Rényi entropies kind of take the same range of values. And yeah, again, we maximize this kind of linear transform of the Rényi entropy over s between 0 and 1. Yeah, so these are kind of known results. It's kind of the background on which the following question is asked. What happens if our hypotheses are quantum channels? So first of all, before we go to the asymptotics, we have to consider what does it even mean to distinguish quantum channels. So a quantum channel, that's just a completely positive and trace-specific map. So I assume you all know that this is kind of the largest uncontroversial class of quantum dynamics that's obtained by unitaries attaching ancillas to your system, doing a unitary tracing out the ancilla. So these are kind of physically motivated and well behaved. And well, when you think about it, okay, I mean, it's a transformation, right? It's kind of to make a test. It looks reasonable that the most general thing is you have to prepare a test because you have to plug something into the unknown channel. And then at the end, you get a state. So the kind of the unknown channel is mapped into an unknown state, one of two, to be honest. And then you measure this. So you can by preparing this probe state rho, and I draw this kind of box here with a question mark, so you don't know if n or m is inside. It's transformed into this hypothesis testing between two states, and obviously the optimization is not only over the measurement but also over this state.
So I have a question here, Andreas. Yeah. So someone is asking, is there a connection between the quantum and the classical hypothesis testing in the same way as in metrology? That is the quantum case just an optimization over all possible POVMs of the quantum state, and then you treat the problem as the classical case?
Well, okay, sorry, I'm going in the wrong direction. Yes and no. I mean, it's I mean, I guess to apply. Okay, let's maybe the more interesting answer is to say no. There is a subtle difference, I would say, because if you would like to apply classical Stein's lemma or Chernoff bound, you would need independent samples. So you need to turn your tensor product of states into a product probability distribution, in fact, an IID distribution to apply, like to take as a black box the existing classical Stein's lemma. So they would suggest I make first a measurement on each of the n copies of the state, so that rho is turned into a probability distribution P and rho tensor n into the P tensor power n distribution, and sigma is transformed into some Q and sigma tensor n into Q tensor n. And then I could apply the classical Stein's lemma, but then I wouldn't actually get this exponent here. I will get something which is called the measured relative entropy. If I insist to base my decision on, so to speak, single copy measurement outcomes. So it's essential for this result that the measurement that I allow here is an arbitrary measurement collectively of the n copies. It has to be entangled, and to obtain this strictly larger coefficient. And the same will be true for the Chernoff bound.
Okay, thank you.
Yeah. So but this is it's a very apt question. The choice, I mean, ultimately, of course, the role of the measurement is to bring us back from this quantum world into classical values on which we base our decisions. It's kind of, the question is only sort of how you, I mean, I interpret the question whether you can compartmentalize this, whether you can just, make some type of measurement and then base your decision. So that's in that sense, of course, it's true that, okay, in some sense I do apply classical reasoning, but the actual analysis to get to these theorems, to these classical results, is rather more direct. This might be surprising. Okay, yeah, let me get on with the channel case. So maybe I go here. Yeah, so we can prepare this state, an input state, and I want to use my quantum abilities. Obviously, I'm allowing myself, as an experimenter, to produce another system, a reference system, and make an entangled state or an arbitrary correlated state between those two systems. so that the channel only, the unknown channel only acts on one, but not on the other. So the most general state I can make using the channel is this one, n tensor identity acting on rho, or well, if it's the other hypothesis, m tensor identity acting on rho. And yeah, so it's the same rho, but then of course I get two different output states here after the channel, and then I apply again the measurement. So I have a double optimization now. If I want to optimize some function of alpha and beta, I need to optimize over rho of states and m over measurement operators. And that doesn't bode very well, because that looks, I mean, unlike the previous one in the case of the discrimination between states, that was just a semi-definite program. I mean, like we had rho and sigma, I mean, we had our two states fixed, and then we just had to, I mean, the linear function of m, both alpha and beta are linear functions of m, and m is subject to semi-definite constraints. So it turns out also this one here, the joint optimization over all states, rho, and all measurements can be cast as a semi-definite program, which is kind of nice. I'm gonna get there actually in the more general setting once we go to n copies, which I want to start now. So the important thing is, the first important stage is now we want to distinguish somehow between two classes of strategies or of approaches to distinguish n channel uses. So one way of looking at it is that, well, it's like a state. N channel uses is just basically one big channel, n tensor power n, which is a channel acting on a big n-fold tensor product of A mapping to a big n-fold tensor product of B's. And so that's just another pair of channels. And so the picture would look like this. I need to prepare some kind of probe state that is kind of a correlation, potentially a correlation between A1, A2, all the way to AN and my reference system. Then on the AIs, I apply the channel, whatever it is. I mean, in all of the n, the same channel. And then I get an output state here, which is just as before. It's like this channel, tensor power n, tensor identity acting on my rho. And then I have two possible states, and I can try to distinguish them. And so I claim that, or I refer to existing literature actually, that the joint optimization over this probe state and this T2 in this measurement is a semi-definite program. So in that sense, in some sense, it's kind of well behaved. I mean, we can hope to get out something from this optimization program, because we have duality, we can do numerics. Before we go up to this SDP part, which is actually not going to be not so important for the present talk, luckily. So let's consider that we could actually do something a little bit more general, and that's the adaptiveness. We could use the channels literally one after the other. And so this is, the drawing is this one here. So I didn't even try to write a formula for this, because it's this long product of maps all plugged together. But I mean, operation is this: you prepare a state that's correlating only A1 and R1. Then you apply the channel, you get a B1. Then you massage this output state this intermediate state that you have here, and you get an A2 that you plug into the second use of the channel, and so on, until at the very end you use the channel n times, because there are n black boxes, and now you get some state that you can distinguish. So why is it more general? Because when you go back to this picture here, you could just, instead of applying all the channels in parallel at the same time, you could literally first apply A1, and then once you get B1, then you apply the second channel to A2 that you have prepared already, and then you apply the third channel to A3, and so on, right? So this, just by staggering the channel uses temporally in this drawing, I hope that it makes sense to you, that to read this as a quantum circuit where the information flows from left to right. You get a special case of this picture, but it's a very special case because I have prepared all of those input states already before, whereas here I'm allowing to do something non-trivial between one channel use and the other one. I could, for example, make a partial measurement to extract some information already, and based on that, prepare the next input state. But that turns out to be actually the worst kind of strategy. What you will turn out that what you really want to do is something quantum. You want to preserve some quantum information to actually get an advantage out of this kind of more complicated strategy. Now this
So sorry,
yes.
I have like I think there may be two questions here.
Okay.
Well, there's a point from Rafael. He says, this is the same class I considered in quantum metrology.
Okay.
And then there's another question. Someone is asking, so your TI stuff in between the channel applications, can they involve doing controlled operations to ancilli that are later measured at the end of the protocol?
Indeed, yes. So these R systems, these R1, R2, those are kind of at the discretion of the experimenter. The experimental design involves choosing what these R systems are. These are kind of these ancillary systems. It involves choosing rho, and it involves choosing the quantum channels TI.
Okay.
And so, yeah, the final output state here, just before the measurement, that's this multilinear function of rho, T1, T2, etc., because it's just by multiplying together super operators. And then I'm multiplying finally with the measurement to get alpha and beta. So again, it's clear that I can write down, I mean, I can optimize, I don't know, alpha plus beta or something, but a priori it looks like a multilinear optimization problem. And so kind of one of the basic, very, very important insights in general about this whole thing is that this can be recast as a semi-definite program. In fact, we don't even have to worry about the precise rho and T1 and so on. Those are kind of folded into something which is called here a quantum comb or a causal channel or a memory channel or a super channel in the works of Kiribella et al. And of many other groups in the past. And so the overall effect, again, what this test does to our channels is just some big object C, which is literally a channel itself. It's a CP-TP map with many inputs. All these B systems are inputs to this comb, and all the A's are outputs. And I make another output X, which is this binary system. So if you want, it's a qubit that goes at the end that tells me which of the two hypotheses I'm opting for. And it's a CP-TP map with some additional conditions that make sure that the later stages of the protocol cannot influence the earlier ones. And so that's a no signaling condition, no signaling backward in time, if you want. And so mathematically, that's expressed as a property of this CP map. So I don't know if I go into it. So that if you trace out later outputs, like if you trace out the last X and maybe some of the AN minus 1 up to some point, then you get a channel that simply doesn't regard the corresponding inputs that come later. So I get some channel Cn that maps only the earlier B's to the earlier A's, tensored with a partial trace of all the other B's that come afterwards. Yeah, so I mean, the simplest case is I'm tracing over X here. If I trace out the output on X, whatever this thing does, it doesn't depend on Bn anymore. So I have an effective channel from B1 to Bn minus 1 to A1 to An, tensored with a partial trace over Bn. And so this is true then for all those cutoffs T. And so this just, I mean, big CP-TP map is given by a semi-definite problem thanks to the Choi-Yarmikovsky isomorphism, and then these no signaling conditions, they are just linear conditions on your map. And so
I think there is a question on this, but this might be just what you just answered.
Yeah.
So Rafael asks, is the semi-definite program a single semi-definite program or an iterative one?
It's a single
but
one.
it's just a single one, and now
so
it's
the variable is this C. That's kind of what the Choi matrix of C, that's kind of positive semi-definite, and then this thing in the yellow box that translates into a bunch of linear conditions that kind of include, for example, the Choi condition that if I trace out over if I take the Choi matrix, if I trace out all of the outputs, I get the identity on the B's. Kind of this sort of thing. But yeah, I mean, it's nice to think about this, but it turns out for the rest of the talk, it's actually not that important that we work with a semi-definite program. It's kind of, it sort of just helps to think about, well, it's a sort of a well-controlled optimization problem if I want to optimize any linear function of alpha and beta. Okay, so that was enough abstract stuff. Let's look at an example, which is not even ours. So in the paper with Farzin and Masahito, we quote this one. It's a very important example for us. It goes back to Aram Harrow, Hasidim, Debilung, and Wojos. They made this together, and it's kind of these are two very concrete channels that have very nice properties, interesting properties that they observe already in that paper from some years ago. They're both so the two channels, obviously, because we want to discriminate them. They map 2 qubits to 1 qubit. And so the input qubits are A and C. C is kind of the control. As you can see from this drawing here, the control qubit is going to be measured, and the outcome used to do something on the target qubit, on the maps A to B. And then the control is thrown away. So the control is only present at the output indirectly because it's used to do different things to A. And so what it does is, okay, so both channels do the same thing to the C register. They measure in the computational basis. They get outcome 0 or 1. Yeah, so this symbol here on the end is kind of, then later we throw away this C. It's not part of the output. And then C is used to choose the channel acting on the qubit A mapping to B. And so when the choice is 0, the channel, actually either channel, acts as a state preparation. So N0 of rho is always the 0 state. The computational base is 0 state, and M0 of rho is always the uniform superposition of 0 and 1. And if the control qubit is found to be 1, then the channel acting on the target qubit acts as a measurement, followed by a state preparation again. So in the case of N, it's the measurement in the computational basis. If we find a 0, the channel prepares a 0. And if you find a 1, if you measure 1, it prepares the maximum mixed state. And and so similarly, the M channel, it measures in the conjugate basis, in the plus minus basis. If it finds a plus, it prepares the 1 state. And if it finds the minus, it has again the maximum mixed state. So both of them are entanglement breaking channels. I mean, I describe them to you as measure prepare channels. And in fact, they are even more. They are so-called classical quantum channels. But there's a kind of a subtlety, namely the basis in which the measurement is made is different for the two channels. The N channel measures both C and A in the computational basis and then prepares an output state, whereas the M channel measures C in the computational basis and A in the conjugate, in the Hadamard basis, and then prepares an output state. So they are very specific, I mean, very narrow, from a very narrow class of almost classical channels, and yet they do something very interesting. What Aram Harrow et al. They observe is just 2 adaptive uses of these 2 channels can discriminate them perfectly. We focus on that first because that's kind of the fun part. What we do is we use the 2 channels in the 2 different modalities. In the first one, we use it to prepare a state. Of course, we don't know which state, but it's one of 2. And the second one, we use it to make the measurement, one of the 2. And so how does it go? So we prepare this here as a 0. Here, this input doesn't really matter because when we put a 0 here, the input is obliterated and replaced by a pure state. Namely either the 0 or the plus state, depending on which of the 2 channels we have. And then we put the 1 here, and we feed this output state directly into the next channel. Why? Because we know that if you put the 1 in the control, the channel will make a measurement either in the computation basis or in the complementary basis. So as a unified description, it makes a measurement in whatever the state is, phi and phi orthogonal basis. So 0, 1 or plus minus. And then we get a computational basis state in either case. When you go back to the description of the channel, namely we get a projection of 0 if the channel was N, well, sorry, if both of the channels were N, and we get x equal 1 if both of the channels were m. And then we are perfectly happy because we can perfectly distinguish those two orthogonal states. On the other hand, what the point of the paper of Aram et al. Was that they showed that if you only have access to n tensor n as like a big channel, then you have to provide one big input versus m tensor n. So this is non-adaptive use that I showed in the first diagram. They showed that the error probability alpha plus beta will always be positive for all n. And so you can definitely never get equal to 0. And so the only mystery about this paper is why didn't they actually bother about finding out what's the scaling of this error probability? Because they had some sort of linear algebraic argument that, okay, it cannot be 0. And so yeah, we're gonna go now. We're gonna come back to this example, but before that, I want to go through some of the no-go theorems. I think there was another question, but I don't know if I should answer it now.
I think there's a point from Rafael saying, so this is a sequential scheme with no true non-trivial adaptiveness.
I don't know what you mean by non-trivial. It's definitely sequential, but yeah, it's of course adaptiveness in the sense that I don't have to do actually anything to the state, but of course that's because the channels are designed in such a way. I mean, we could the channels are already in such a way that the output is kind of prepared for this protocol to work. Yeah. So of course, this intermediate T here is kind of almost just the identity. Yeah, that's true. And I don't even have a reference system, right? I don't have an ancillary system, which is kind of natural because I have these CQ channels here. But I mean, anyway, it's sort of just a toy example to see what kind of thing can happen. Can I go on? So before I come back to this example in more depth, I would like to just get over the no-go theorems. So like when adaptiveness in doesn't really help significantly beyond non-adaptive strategies. And so this all on the level of these asymptotic exponents. So in separate papers, I mean, Wang and Wilde figured out what is the Stein's exponent for adaptive strategies. So I mean, this kind of inside here, this bracket, I consider all adaptive strategies such that the error probability of the first kind is bounded by epsilon, and I think I have to assume it goes to 0 for this theorem to hold. And then I'm interested in the minimum beta and how it scales exponentially. So I take the log divided by n. This limit is equal to something called the amortized channel divergence, and it's this beast here. So this kind of really interesting, like the channel divergence is down here. You're just applying the channel to a probe state, which can have an ancillary system. So there's a row RA, and R is whatever. And then we are looking at the relative entropy between the output states, n of rho versus m of rho. And in the amortized case, we're looking at two states that we have rho and sigma, which might already have some in their difference, so the relative entropy will be non-zero. And then we're looking at the n of rho versus m of sigma minus relative entropy between rho and sigma. And we take the supremum over all pairs of rho and sigma. So as far as I know, nobody knows how to calculate this, but as a sort of information theoretical result, it's kind of very satisfying that this should be the exponent. And then for the non-adaptive strategies, it's kind of, I don't even have a source here, but I think it's sort of, follows from the previous Stein's lemma that the exponent should be the regular channel divergence, except that it turns out to be not additive in general, so you have to take the regularization. So again, nobody knows how to calculate this, but again, from an information theoretical point of view, it's sort of satisfying that, yes, there is a kind of a relative entropy quantity here that rules this Stein's lemma. So the amazing thing is these two exponents are the same, which was not obvious when those two results were formulated, and was proved in two different ways by Fang et al. So that's Fang, Fauci, Renner, and maybe Mario Berta. Okay. sorry, I forgot to put all the names, and this bites me now. So they invented some chain rules for these relative entropies, and they proved that these two numbers are the same. This regularized channel relative entropy is equal to the amortized channel relative entropy. And then Berg et al. In a more recent paper, they showed how to turn directly an adaptive protocol into a non-adaptive one with the same asymptotic exponent of the second variable of second time. So it's very interesting subtle point, because the error probability itself is not preserved. It kind of it suffers a little bit. So the same pair of alpha beta is not attainable. If it's attainable by adaptive strategy, may not be attainable by non-adaptive, but the asymptotics is the same. And so in our paper with Farzin and Masahito, we show that in the special case of classical quantum channels, where the classical quantum channel means that the two channels measure in the same basis, orthogonal basis, and based on the outcome prepare an output state. We show that none of those asymptotic exponents show any difference between adaptive and non-adaptive strategy, which is kind of, I mean, it's kind of intuitive why these CQ channels, and maybe even more fully classical channels, which is the case when all of the output states, rho x and sigma x, commute pairwise, why that should simplify the analysis. I mean, first of all, in the non-adaptive case, you just have to provide an input to the channel, because the channel measures in some computational basis. It's fairly easy to arrive to the point that you don't need any ancillary system, and you should simply prepare one of those X input states. Just try to find the optimal classical input to your channel. And the adaptiveness somehow also doesn't, I mean, why it doesn't, I mean, it simplifies, first of all, what the adaptive strategies should do, because you have to produce always an input to the next channel. And so that means you have to make partial measurements on the previously produced output states. And so that is somehow intuitively responsible for the fact that there is no asymptotic advantage. And so let me just show kind of what you get. I mean, in the non-adaptive, so parallel or non-sequential strategies, I argued intuitively that, well, basically we are reduced to simply finding the optimal classical input, because that turns your your channel into a pair of output states, and it's from this finite list, rho x versus sigma x. So it's for the Stein exponent, well, that's the relative entropies. You just should find the maximum relative entropy between pairs of output states corresponding to the same input, of course. And the same thing for the Chernoff. You can use x to prepare a pair of output states. Okay, you just maximize them. And because the channels are product channels, you don't, and because they measure in the computational basis, there is no question of entanglement helping. There's kind of, yeah, that's it. And this, and even the same thing for the Hoeffding function of R. And so, yeah, so the second theorem is this kind of no-go theorem, that when we stick to these classical quantum channels, there is no asymptotic advantage of adaptiveness in any of those settings. The adaptive Stein's exponent is equal to the parallel Stein's exponent, and the adaptive Chernoff exponent is equal to the parallel one, and the adaptive Hoeffding bound is equal to the parallel Hoeffding bound, which are given by these simple functions. And yeah, so I'm not going to prove that here, because that's sort of, I mean, it's unfortunately it's a truly asymptotic result, but it's intuitively it's because the adaptiveness somehow destroys precisely the quantum nature of your output state, and you need to extract classical information to produce some new input, and that is ultimately turns out to be not helpful. Okay, so I think I'm a bit late, so I'll have to maybe speed up, even though that's the part that I like most. Finally, I want to show something where the adaptive strategies do result in an asymptotic advantage that survives the asymptotic limit. Obviously, we have to do that in the Chernoff or Hoeffding setting, not in the asymmetric one. And it has to be some sufficiently quantum channel, which turns out the one of Harrow et al. Is already one of those. So we start with a very simple criterion that Roniao et al. Had that generalized the argument of Harrow et al. For guaranteeing that alpha plus beta case positive, so that at least one of the two error probabilities must be non-zero for all parallel strategies. Then it goes like this. They observed that if you write the two channels in Krauss form, and you choose any Krauss compositions with Krauss operators EI and FJ, you form this span of EI dagger FJ. That's kind of a curious object. If that happens to contain a positive definite matrix, not semi-definite, but definite, positive definite, with non-zero, only positive eigenvalues, then it follows that alpha plus beta is positive for all n and for all parallel strategies. Oops, there's more questions, but I'll just continue. And so like, I just want to show how to make this quantitative, and so that we can apply it to get some bound on the Chernoff exponent. So if we you look at a single shot strategy, so we prepare a state without loss of generality. It's going to be a pure state between the system and the reference, and we get rho AR or rho BR and sigma BR as the output states. Alpha plus beta happens to be the optimal alpha plus beta, if you optimize over the measurements, happens to be just this. It's 1 minus half the trace norm of rho minus sigma, these two guys. And so we're going to use a very simple lower bound for this. Duan et al, they just wanted to show it's positive. Okay, we just use a lower bound that will imply it's positive. We use the lower bound that this quantity here is lower bounded by the fidelity square. And I don't know, I don't remember where the half comes from, but I think that's because there's a square root somewhere. Did I have this before? I might have deleted the slide. And so here's the quantitative lemma. If there exists linear coefficients, complex coefficients, which I have to normalize to get something meaningful, so the sum of squares is 1, such that this linear combination of the EI dagger of Fj with those coefficients gamma ij is positive definite, so it has a minimum eigenvalue, then alpha plus beta is lower bounded by this function here, the 1/2, the 4th power of the minimum eigenvalue. And so because I can apply this now for n-channel uses, I get the corresponding tensor product, Gauss decomposition. I can use the tensor product or the Kronecker product of the coefficients. I get this lower bound. For n parallel uses, I get alpha plus beta is 1/2, lower bound by 1/2 the 4nth power of this minimum eigenvalue. And so that gives me an upper bound on the Chernoff coefficient. So let me see.
Just sorry, Andreas, to interrupt. So there was a question by a PhD student, Homo, on a previous slide. He just asked, will the classical quantum channel be similar to a noisy quantum channel?
It's a very special case. It's a very special case because the way I look at the classical quantum channel is it is a special CPTP map. It's a noisy quantum channel, but with this particular structure, that what it does is it measures in one chosen computational basis, and then based on the outcome prepares a state on the output.
Right.
So it's basically given entirely by this basis and by the list of output states.
So it has a very, very specific form of noise.
Exactly. As a CP map is a very specific structure, and it's true that in some of the older literatures, like Holevo and all the way to Hayashi, they sometimes want to think of the classical quantum channel as literally a mapping from a set of inputs to quantum states.
Right.
But I don't know. I think intuitively it's a bit more helpful to think of them as just a special kind of CP map.
Okay, thank you.
Okay. Okay, so here's the brief proof of this. I just want to show, like, it's a very simple-minded idea, and it's essentially just a footnote to Harrow and Duan et al. Simply saying, okay, you can get, instead of just saying alpha plus beta is positive, you get this number, a lower bound, that actually scales exponential with n. So we have our states rho and sigma. We need the partial trace of the probe state, and trace out the reduced state of A. And so it goes like this. We need a lower bound on the fidelity, right? Remember that we had this kind of thing. We observed that the optimal alpha plus beta is the trace distance. And this inequality, I think that goes back to Fuchs and Van de Graaff, that relates the trace distance and the fidelity. The fidelity is this weird thing, is the trace norm of squared rho times squared sigma. So that nobody likes it. We lower bound it itself by the trace of squared rho times squared sigma. And we lower bound that again very brutally by simply the trace of rho times sigma. Very bad lower bound when rho and sigma are highly mixed states, but I don't care for the moment. So then it's just like, then you plug in the form of rho and sigma because they are obtained from the same state phi by applying the channel, and you plug in the Krauss operators and you get this here. By a bit of algebra, it's the sum over all ij trace ei dagger fj times tau. And so by Cauchy-Schwarz inequality, that's where I can introduce those coefficients gamma ij. I can lower bound this by this a big square of a sum of ij, gamma ij, etc., etc. And so inside here I have my projector, my operator p, that is positive. So I get trace of tau times p modulus square. Well, the modulus I don't need at this point because p is a positive, tau is positive, so the trace is a positive number. And in fact, it's lower bound by the minimum eigenvalue squared of p. And so I plug it all together. I get alpha plus beta up to this factor of 1/2 is the minimum, is lower bound by the minimum eigenvalue of p to the power 4. And so simply applying this to n tensor m and m tensor n and the tensor products of the Krauss operators and gamma tensor n, we get the operator p tensor n, which has minimum eigenvalue lambda min of p to the power n. And that's it. So very simple argument. And well, okay, I wouldn't have shown you this example nor the lemma if the two wouldn't apply to each other. Turns out, Harrow et al.'s example, I mean, you write down the channel, you can figure out what the Krauss operators are. It's a simple exercise, or if you don't want to do it, look in our paper, in the preprint, we list the Krauss operators actually. And you can form a positive definite operator, and it's a bit of a game what kind of eigenvalue you can get. I mean, we get a really awfully small eigenvalue, but it's positive, and it gives us an upper bound of some number, 13 point something, for the parallel Chernoff bound. But previously we argued that two uses of the channel already give us perfect distinguishability. So that means the adaptive Chernoff bound is infinite. And so another class of example comes from a very beautiful paper by Gravietz, Pavela, and Buchawa. They look at, these are also entanglement-breaking channels. They are so-called QC channels. I mean, what this is a channel that takes a quantum system and outputs something classical. So in other words, a measurement. So the channel N and M, each of them is given by a P of M on a Q trit, if I remember correctly, in the example that we quote, with 9 outcomes. It makes the measurement, so this is the probability of observing I, and then prepares an orthogonal state I to record the output. And so we take two such POVMs from this Gravietz paper that are perfectly distinguishable with two uses or with some finite number of uses of the channel. But then our lemma applies and gives a lower bound on the error when you have only parallel uses. So a little detail about this example from that paper is that it's actually the same POVM, only that the outcomes, the measurements are labeled in a different way. So the I's and J's are related by a permutation of the outcomes. It's hilarious when you think about it, but that's enough to make them non-distinguishable by parallel strategies. Yeah, so Gravietz et al. To know that those two measurements are then to prove that they are distinguishable perfectly, and then we get that the adaptive Chernoff bound is infinite. They use a little observation by another paper from Yadwan et al. And a subsequent paper by Nang-Kun Yu and his colleague Zhou, and it goes like this. So the second paper shows the following: the adaptive Chernoff exponent is infinite if and only if there exists some finite n and an adaptive strategy of n channel uses such that the error probability is 0. Yeah, so in that case, obviously, we will declare the Chernoff bound to be infinite. But of course, it could be infinite also if alpha and beta go to 0 in some kind of super exponential way. So Yu and Zhu show this doesn't happen. If the limiting exponent is infinite, it's because at some point, at some finite n, alpha and beta become strictly 0. And then this thing here, Duan et al. Have characterized. It's this here. This condition is that the span of this EI dagger Fj, which turns out to be a very important subspace for this game, doesn't contain the identity, and the Choi matrices of the two channels have disjoint support, so they intersect only in the zero, the subspaces. It's a criterion for this second thing to happen, and it's equivalent to this Chernoff exponent equal to infinity. Okay, so this is my final slide. So yeah, after having kind of this recent history of essentially no advantage, no-go theorems, where the adaptiveness, despite being so beautiful, doesn't really result in anything, we find at least some small class of channels, and in the binary hypothesis testing case where the adaptiveness does help. And yeah, I would argue that the adaptiveness requires somehow a genuine quantum channel, in the sense that a CQ channel is not sufficiently genuine quantum. Somehow the fact that it destroys any kind of superposition in the computational basis, that doesn't cut it. So the interesting thing is that the Harrow et al. Example are also CQ channels, but unfortunately not in the same basis. Yeah, so each of them individually qualifies as a classical quantum channel, but they are not in the class of CQ channel discrimination, because the classical measurement, the measurement at the start of the channel is not the same, as I pointed out. And then the Gravietz et al. Example shows that also quantum classical channels are also sufficiently quantum, and it's enough somehow that you have a quantum state at the input, which you can entangle with a reference system. It doesn't matter that it's destroyed. I mean, obviously this happens because the quantum measurement is highly non-orthogonal. It's not a basis measurement in Gravietz, Pavela, and Puchawa. Yeah, so there are plenty of open questions there. Obviously, this is the whole paper is kind of a case study, because I mean, binary hypothesis testing is considered to be the bedrock of hypothesis testing, but it's not the only thing. You can have multiple hypothesis testing. You can have composite hypothesis testing, where each one or both of the hypotheses is not just a single channel, but maybe a set of channels. And another question comes from kind of looking at these combs, because when I think it goes back to the work of Keribella and his collaborators already. They noticed that if you want to have kind of an object that embodies a measurement on a bunch of channels, a comb is not the most general thing, mathematically speaking. Mathematically speaking, there are these kind of processes. Sometimes they're called process matrices or non-causal channels. They are the mathematically largest set of linear functions that are guaranteed to map a bunch of channels, and like a sort of a product of independent channels, a product of independent boxes, into a probability distribution. And so you can ask the same question again. So what about the possible advantage of these kind of strategies compared to the adaptive or the non-adaptive ones in any of those asymptotic settings, Stein, etc. As far as I know, we really don't know anything about this. We know that in the finite n, in like 2 copies or 3 copies, the adaptive, the non-causal strategies, they can make small improvements to the error probabilities, but we don't know if they survive in the asymptotic limit. And I think I better stop here because it's already past 1 or past 12 in your place. Thanks.
Thanks a lot, Andreas, for a great talk. I think, as Hugo mentioned in the beginning, if anyone has more questions and stuff like this, pop them in the chat or in the Q&A section, and we'll read them out. I have a first question from one of our PhD students who's asking if you can give some examples of applications of hypothesis testings. Is it used as subroutines in quantum algorithms? Can it be used for quantum sensing? What's the killer application?
No, well, I would say probably, I don't know if yeah, I'm not such a big expert in sensing. I mean, that's, I feel like most of the applications of sensing have more to do with estimation, with like, estimating some parameter. Hypothesis testing is something much more basic in statistics, right? Like this kind of language of null and alternative hypothesis. This is about, for example, I don't know, you run a new experiment on the Large Hadron Collider, and I mean, as always, the objective is to refute the standard model. And most of the time you don't. And so you have to design your tests, and the tests are designed as hypothesis tests. It's like you definitely want to recognize new physics. You have some new idea where the new physics might be, but above all, you don't want to needlessly reject the standard model, because that's all you have. So it's that kind of setting. Then the kind of, I mean, when you talk about applications, I think you really always want to consider more complicated hypotheses, multiple hypotheses. This maybe not just two, but it's an idealization. It's good. And then mathematically, applications of this are really in information theory. And from my perspective, information theory, a lot of the basic stuff like that in the textbook relies on mutual informations and entropies, really is about hypothesis testing. And the famous Shannon formula for how much information can transmit over a noisy channel, that can be interpreted as via hypothesis testing. And so this kind of it's a building block to do information theory. This kind of, for example, this discrimination between multiple channel hypotheses. This has something to do with quantum reading, where you I forget who invented it. I think it says Lloyd and must pioneer this, and also Stefano Pirandola up north in the UK. Where you think that your information is encoded in a device, I think the example they give usually is like a CD. It's the different fields on the CD that the reader can distinguish. They are basically different materials, and by preparing a state, shining in some light and looking at how it reflects, you try to read out this information, which of the different material states is there. So they're kind of mathematically different channels. And so this thing with the adaptiveness, it pops out there as well. As far as I know, it's still an open question whether a quantum compact disk, so to speak, would benefit from an adaptive readout strategy, or whether it's better to just shine in light everywhere at the same time and absorb all the reflection in parallel.
Interesting. I think we have Rafał on the call if you want to ask some questions live.
Yes, can you hear me?
Yeah. Hi.
Okay, great. Thanks a lot, Andreas. I learned a lot. So I'm just trying to make more connections with quantum metrology. So I was thinking, because I mean you have two channels, and now if I want to understand really for what kind of examples I can expect this adaptiveness gain, I wonder if, for example, you could think of a case where I have two channels that differ by some small unitary rotation. Yeah. And then can I exclude this gain, or maybe we can have some examples where there will be this gain present, or from this condition you gave in the end, maybe it's clear that it is not so, or I don't know. I mean, maybe it's clear because Krauss now I see. I think Krauss operators would differ by unitary. Does it mean that trivially this identity will be inside this?
Oh, yeah, well, it might. Okay, I mean, obviously, this was for the purpose of the mathematical argument that one of the two strategies gives you perfect performance. But I mean, obviously, from that you can see that you will generically also have situations where you just have two finite numbers, but different. Then it might happen like this. I mean, if it's basically just like basically the same channel followed by one of two different unitaries, maybe this is ultimately related to this discrimination of just unitaries, which is well understood in the.
But the channels may be very noisy. Yes, I mean the channels
yeah,
themselves
exactly.
may be very noisy. Okay, so it's not obvious.
There you might
yes?
be able to argue that the adaptiveness doesn't help, because the unitaries themselves already, we know that the adaptiveness doesn't do anything.
Yes, but okay, here it's not so clear. I think.
Yeah, sure, because then there will be a finite error probability in general.
Mhm. Okay, thank you.
Yeah.
And I can see there's another question. Sorry.
I want to, as a disclaimer, I mean, obviously the examples are kind of reverse engineered. They're kind of the two examples that we have discussed. They come from people figuring out this necessary condition of Tuan et al. They say, well, okay, how can I make it such that the channel can be distinguishable perfectly by some finite uses of the channel, but and then you just work with it. So they are a bit artificial. Conversely, I don't really have a good sense of, for a sort of a generic pair of channels, will I see the distinction or not? That's wide open for me at least. Okay, sorry.
I think there's just, well, let's see. So there is one question which has to do with the underlying quantum resource of the advantage. So the person asking the question says that in, for example, state discrimination, people have linked the quantum advantage to contextuality. Are there similar links to quantum resources for the scenarios you have discussed in this talk?
Oh yeah. I mean, I think that's a very interesting point. But I mean, I think it's resources in a more mundane sense of like quantum information processing. I mean, you have to ask yourself, what kind of quantum device do I need to realize those strategies? And for example, even for the parallel strategy, that looks actually in some sense the more daunting one, because you have to prepare in one go a big entangled state potentially, and then also at the end you have to do some enormous collective measurements. So that is kind of the sort of resource you're looking at for the non-adaptive strategies. And if you want to limit those resources, you would like to limit, for example, the degree of entanglement in the initial state preparation and the final measurement. And for the adaptive strategy, when you look at this diagram, that I don't want to go back because it's too many slides, this staggered diagram, you need long-term quantum coherence. You need a quantum memory that kind of preserves a quantum output state and manipulates it into the next stage all the way until the last end. And so that's its own, that's maybe that might be ultimately just a single qubit, but it has to survive a longer time. In the example of Harrow et al., it's one time step. You have to kind of feed this output state intactly as an input to the next channel. So kind of there will be some sort of that's some information processing. You just have to preserve the state for some minimum of time before the next channel can act. And so that also is a kind of a resource. I mean, Harrow et al., it's just two uses of the channel, but if you can cook up a setting where you really need some large number before the effect manifests itself, that itself is a resource, because you can link it to the quality of your quantum memory, basically, and the information processing. So I would put it more like this. I mean, the contextuality, that sounds more like a much more fundamental sort of thing, but yeah, to me it's more to do with what kind of quantum computer would I actually need to see that. I mean, for some people already the existence of the ancilla is a problem. I mean, like, may I take a bit of your time? So at the end of Raphael's question, we talked a little bit about the discrimination of unitaries. It's a well-known fact that two unitaries are always perfectly distinguishable if you have sufficiently many copies available. I mean, sufficiently many invocations of the black box. You can do it in parallel, but then you need an ancilla. You need to make an entangled state, and it's a sort of GZ type state. Very, very bad in terms of our current capabilities. Whereas the adaptive strategy is literally just preparing a suitable pure state. It has to be a superposition of the eigenbases of the unitaries, of some unitary, and then applying the unitary multiple times. Just a long string of the same unitary acting. And then you are guaranteed to find one of two orthogonal states. So it looks like the adaptive is actually easier. It uses less resources because we don't need to make this giant entangled state that will go here immediately. So it's a very interesting thing. Like, I mean, the way I talk about it, mathematically, adaptive strategy is the more powerful one, or the class of adaptive strategies. But when you look at it concretely, as given adaptive strategy might actually look less challenging than a given non-adaptive one.
So I think that also answers the last question I can see in the chat, where someone asked if the take-home message is that one should do the non-adaptive one because it looks easier. And I think
yes, exactly. Yeah, sure. Totally.
Okay, Andreas, thank you so much for this wonderful talk. It was, I think, a perfect kind of review of the field and a collection of new results. That was really
nice. Cool. Thanks for the many questions. It helped me get through the talk too.